To this point in the course, we've been looking at evolution at the level of individual genetic loci or small numbers of them, maybe 2 at a time. In this final piece, we will back out to develop the population genetic theory for the evolution of continuous quantitative phenotypic characters, where the story is that of influences from alleles at many genetic loci, so-called polygenes, and also these traits tend to be ones where effects of the environment play a very important role that needs to be included in the model. Most ecologically important quantitative traits, really all of them, vary. And our starting point is to describe that variation. Then the goal is to explain it. Distributions are very often unimodal and approximately normal, as with these distributions of height for this group of men and women in an evolution course who are making a living histogram of human stature out on the football field at the University of Connecticut, which you can tell because there's the Yukon logo, which is a helmet with Yukon written on it. The other feature of quantitative traits that is central to their study and part of what we wish to explain is that offspring and parents tend to be correlated. You simply assume that these tallest women, for example, tended to have, at least in general, taller than average parents, as did these tallest men. So what's the explanation? It is, as I said a moment ago, independent contributions by genotypes at many loci, that is all throughout the genome, typically, and by random environmental influences. And those are the elements of the theory of quantitative trait variation and evolution that we're about to develop. Gillespie's chapter, as always, is well worth reading, written in his very spare style, and here's his remarkably spare and colorless personal example, figure 6.1, which is taken from data he gathered 1 year in his own evolution course, where he had the students report their own heights and the heights of their parents. The left-hand figure is just a histogram of sorts, describing the distribution of heights of all the students, and there it is, unimodal, and given its smallish size, close enough to normal. And here's the plot that gets at the heart of the matter. It shows how the offspring, the students in the class, and their parents are correlated. And Gillespie has here taken out the effect of the mean and plotted both the mean height of the parents, that's simply the average of moms and dads' heights, as deviations from the mean of the parents' heights. And likewise for the students, he's plotted their heights as deviations above and below the mean for the class. Necessarily, then the joint mean is the place where the regression line passes through and rotates, and the slope of the line, as we'll see, is an estimate of what's called the heritability, a key parameter that gets at the correlation between parents and offspring, which is a product of these polygenes we're to develop. So what is a quantitative trait? Let's first deal with that. It's absolutely anything that you can measure on a scale with units of some kind. And yes, you can make them up. Some examples. Much studied, of course, are morphologies like human stature and other measures of size or shape of anything. A much studied case that we'll come back to briefly is that of beak dimensions, especially beak depth or height in Darwin's finches in the Galapagos. So here's two birds from the same population, drawn rather accurately. Some at this upper tail of the distribution have these really substantial beaks, much taller, like 12 to 14 millimeters, say. And then there are smaller, usually, more perhaps slim birds with narrower and beaks that are less tall. And the evolution of that quantitative trait, which is of great ecological importance to the birds, has been studied for decades. Physiological measurements, pressures, temperatures, rates of anything are perfectly valid quantitative traits, as are behavioral performances, speed, for example, or puzzle solving. Here are some textbook data on swimming speeds in meters per second of bunches of men and women in some event, presumably. And here's the way IQ is defined and measured, as a very abstract principal components analysis of people's performance on a bunch of paper and pencil tests, which is what it is. It shouldn't be called intelligence quotient. It should be called paper and pencil quiz-taking quotient, but that's another story. Okay, those are all perfectly good quantitative traits, and they all obey these generalizations that we're about to describe, and as far as we can tell, also can be explained, that is, the variation and evolution of them, can be explained by the theory we're about to develop. And I should point out before we leave this slide that fitness itself, however you measure it, or its correlates, number of seeds set, surviving offspring, fledged, whatever, fitness itself is the ultimate quantitative trait. It's continuously varying. You can measure it on a scale of some kind, or indeed many different kinds if you like. And it is, of course, what natural selection is by definition constantly favoring. We'll come back to that idea in a few days. Okay, another preliminary is that most quantitative traits end up being distributed approximately normally. Especially if you have big samples and perhaps after you do some transformation of the data, like taking their square root or log or something. As you know by now, a normal distribution has two parameters, its mean and its variance or standard deviation, which amount to the same thing, again, modulo a square root transformation. The variance is the average squared deviation from the mean, and the standard deviation is just the square root of that. Here are some old data from counts of dermal ridges in fingerprints from the day when lots of effort was spent for forensic reasons on the study of fingerprint patterns. Here's some index of total number of ridges. I don't know exactly how it's defined. I hope that's over several fingers because I don't see 200 plus ridges here. In any event, it's a beautiful quantitative trait with a tail of a few people with very low counts and others with very high counts, most in the middle, with a standard deviation here of around 40 ridges on a mean of something like 145. There are many reasons why normal distributions are natural and favored for modeling quantitative traits. And as we'll see, they arise in a very natural, intrinsic way from our underlying model. But also they are convenient because they have just two parameters, and those can, in a sense, both be eliminated just by normalizing the distributions to be standard normal distributions. And one does that simply by subtracting the mean from every observation. It's just a constant once you've calculated it. So that doesn't change anything really. The mean just becomes 0, as Gillespie showed in that opening slide about the heights of the kids in his class. Then divide every observation by the standard deviation, which is also just a number that describes that property of the sample. So if you do that, then the standard deviation, and the variance both become equal to 1, and we have standard normal distributions. So the upshot is we're always free to do that. It doesn't change anything. The units of measurement are always arbitrary, so we were free from the outset to define the mean as 0 and to use a ruler whose markings were 1 standard deviation apart. That's as good as any other unit of measure, really, for scientific purposes. And then by doing that, we always get distributions that have, well, 68% of the area roughly within 1 standard deviation of the mean, which is also ideally the mode, something like 96% within plus or minus 2 standard deviations, and 99.7 or so percent of all the observations within 3 standard deviations of the mean. Okay, so here are some reasonably large samples of heights again, of females and males. These are special men and women. They're from the Utah Genetic Reference Project, which was a forerunner of the whole Human Genome Project, and a reason why Utah is to this day such a center of human genetics. These are the offspring in large local families that were enrolled decades ago into the genetic study that turned into the Genome Project. And so they're in this sample, I believe, from 36 families that had at least one daughter, at least one female offspring, and at least one male. And anyway, so that's where these numbers come from, and they show all the properties we expect of a quantitative trait, approximately normal distributions, and well-defined standard deviations. Notice they're similar for males and females, even though the means differ substantially. Okay, so we'll come back to many of these traits later when we look at heritability and selection on them and so on. For now, let's turn to developing the conceptual model that was used back in the early 20th century, just about 100 years ago, a little more than 100 years ago, to establish the analysis of variance, among other things, as we discussed early in the course. All right, so here it comes, the simplest quantitative trait model. We imagine the trait is affected genetically by several independent loci, which are independent in 2 senses. They're assumed in general not to be closely linked in the genome, but they're more importantly independent in the sense that each exerts its own effect on the expression of the quantitative phenotype, and those add up to determine the total genetic effect. So we can think of the alleles at each locus as contributing just a plus or a minus, a little boost relative to the mean or expected trait value, or a little decrement. We then assume each individual's trait value, as I just implied, can be represented or thought of at least as the sum of all its plus alleles at all the loci that have effects on the trait, which may be many and is at least a substantial handful. We could also, of course, write the trait value and think of it as the sum of all the minus alleles. That's really the same thing, just with the sign reversed. Okay, so the consequence here, this is a subtlety, but it's very simple, just a new idea for you to imbibe if you haven't met it before. The idea is that a plus allele at one locus, let's call it the A locus as usual, has the same effect, or at least the same kind of effect, as a plus allele at locus B. So they are interchangeable in that sense. There are 2 different ways genetically, I mean completely different in general on different chromosomes, to get a genotype that inclines toward a slightly higher or slightly lower value of the trait. So it then follows just from those assumptions that with random mating, we will get what I will call a quasi-binomial distribution of the number of pluses and likewise of the number of minuses, which are just the same thing. All right, so we'll focus on plus just for convenience and out of habit. So as the number of such loci contributing to the trait, which are polymorphic, that's implied, we're interested in them in any given population because at that locus there are both plus-making and minus-making alleles. As the number of such loci increases, the distributions become more and more smooth and closer to a normal distribution. That's the idea. And so here's a simple textbook example, but it's helpful if you're new to this subject, that shows how this goes. And so we'll just start considering this trait, which is the flower height in tobacco. This is modeled on an actual experiment done just slightly over 100 years ago by Edward East in North Carolina. He was a tobacco breeder, and he had actually a strain of tobacco, Nicotiana, that had relatively short flowers, or corollas as it's called in the trade. That's shown here in this cartoon by these little flowers. And he had another inbred true breeding strain where everybody was tall flowered. And the experiment he did to get at their genetics was to cross these two inbred strains, producing F1s, which were indeed intermediate in flower height, and he then crossed the F1s among themselves to make F2s and asked what happened. Right? We'll see later what really happened. In this cartoon example, if the flower height is controlled genetically by just two alleles, plus, which is big A, and minus, which is little a in this notation, then there's one locus doing all the work. These are heterozygous at that one locus, and then we get 1 to 2 to 1, the usual Mendelian ratio in the F2s. And look what we've got. We've reconstructed the short parental line and the tall parental line, and we have 50% of the F1 type genotype and phenotype as well. And notice this is already looking almost like a normal distribution. It is at least humped in the middle. Okay, so you see where this is going. Now we're going to have two loci. The B locus also has plus and minus alleles, capital letter B and lowercase b. The F1s are double heterozygotes, little a, little b, big B. They're intermediate again. We mate them among themselves. Now we get 5 different genotypes that matter. That is 5 different ways of having either no capital letter alleles, or all capital letter alleles, or 2 and 2. So, and there are 2 ways each of having either one capital letter, it could be an A or a B, or you could have 3 of them, an A and 2 Bs, or 2 As and a B, in which case you're on the shoulders of the distribution, which is looking more normal. And there are actually 3 ways of having 2 and 2 capital letters and lowercase letters. They all amount to the same genetic effect on the phenotype, and so those individuals make the mode in the middle of the distribution, which is close to its mean. And then ... as many loci as you like. The final example in this cartoon has 6 loci, A, B, C, D, E, and F, and the same game happens. The short parent has all lowercase minus making alleles. The other parent, the tall one, has all capital letter plus making alleles. The F1s are half and half. You mate them among themselves, and now what you get is truly indistinguishable from a normal distribution of genotypic effects on the trait. Okay, so that makes a point which I made many years ago in these graphs that just show the point over a broader range of numbers of loci, that as the number of loci affecting the trait increases, the variance relative to the potential range decreases. And in all these cases, the shapes of the distribution are very close to normal because the smallest number I considered was 6. The largest was 400. Right, in the case of 6 loci, you can, with intermediate allele frequencies like 0.5 at all 6 loci, get a very few of the shortest possible and a very few of the tallest possible genotypes in your population. But with 25 loci, 4 times more, say, that's becoming extremely unlikely. You simply don't see the shortest or near shortest or the tallest or near tallest individuals, and the range of variation relative to this maximum possible is much smaller. Increase by a factor of 4 again, you basically cut the standard deviation in half, and the variance even more. Now it's a really tight distribution, and never in the history of the universe do you get the shortest or tallest individuals, and it's even more ridiculous if you quadruple the number of loci again. Now it's just an extremely compact and smooth normal distribution. Okay, so we'll come back to this principle at the very end next week. It has implications about the evolution of quantitative traits. You may think 400 loci seems like a ridiculous number to be affecting some trait, but and when I made this figure, we didn't know. We had no estimates from real genomes of organisms like ourselves. Now we know that actually 400 is a severe underestimate of the number of loci in our own genome that affects height, the favorite quantitative trait of all time. Again, we'll come back to that. All right, so here's the more general model. That was the cartoon, sort of Lego model for how the genetics works. Here's Gillespie's very general way of writing it, which is elegant and abstract, but for some purposes perhaps helpful. So let's take a minute or two to understand it. The idea is mom makes a haploid gamete and gives it to baby, and it contributes a genomic contribution to the trait value, which we will call X sub m for mom. And it has a variance over moms. It's a random variable, what any given mom will contribute in any given gamete. And within the population, there's some variance of this genetic contribution X that moms make, and we can just write its variance as V of X sub n, just to be completely explicit. The dads do the same thing. They make a genomic contribution X sub P for paternal. I guess we should say M stands for maternal and P for paternal. And of course, it has a variance over dads of the variance of X sub P, and to an extremely good approximation, the distributions of the maternal and paternal effects should be equal, assuming this is a random mating population that's been around for a while. There's no difference in the distribution of genotypic effects carried by males and females, except perhaps on the sex chromosomes, which are a small deal. Okay, so this is an additive model, as Gillespie calls it, because then the phenotype of baby can be written, its genetic part, as X sub m, the genetic influence that mom contributed in the collection of quantitative trait affecting alleles that she put into her egg genotype, and likewise X sub p for the contribution made by dad, and those will add because baby gets both of them. And then during the development of the offspring, there will be an environmental contribution, which Gillespie calls Greek epsilon, lowercase. And it has some variance, of course, over offspring, which is just the variance of experience of the world by the individual as it develops. And so there's another random contribution, presumably with a mean of 0. All of these can be written, of course, with their means for the population to be 0 and their values being equally often plus something or minus something. Likewise for the environment, and there's some variance that describes how much the environmental effects vary. These again are environmental effects on the phenotype and genetic effects on the phenotype of this offspring. So that's the model. The phenotype, the quantitative character or trait state, is just the sum of these three contributions. And over the population as a whole, then the variance of the phenotypic contributions or values will be the sum of the variances of the three contributions. The phenotypic variance, which is actually the scale on which we're going to be focusing for most of the time, the phenotypic variance, the thing to be explained, is decomposable, Fisher realized, into these parts: the variance of the maternal contribution, the variance of the paternal contribution genetically, and then the variance of the environment. And these are more conventionally boiled down to V sub G for the genetic variance and V sub E for the environmental variance. Now, an important technical caveat, this additivity assumes the parents are uncorrelated with each other, both in genotypic effects and with respect to environmental effects. Gillespie discusses this on page 198. It isn't necessarily true, and especially in our species, with its elaborate management of environments and so on. It's definitely not strictly true, but for present purposes, it's safe enough for us to assume that the correlations in other species, at least, are small enough that we don't have to worry about them. And to a good approximation, we can think of the phenotypic variation that we see in the population in a given generation as being composed of these pieces that literally add up to give the total. Okay, so now we kind of have a theory for why quantitative traits are normally distributed. It's because each of the three contributions is itself the sum of many independent little causes, genetic in the case of X sub m and X sub p, and environmental in the case of epsilon. And so the central limit theorem of statistics tells us that the sum of random variables will more and more closely approximate to a normal distribution if they are independent of each other. And that's true regardless of how those independent contributions themselves are distributed. They could be binary or uniformly distributed or whatever. We don't care. If there are enough of them contributing to the sum will approximate better and better to a normal distribution like this. Okay, let's take a break here and then pick up after you've had a chance to stretch your mind with the next steps.